All right, should we get started? My name is Morten Rasmussen. I'm with ARM. I've been looking at some scheduler work, and I'm going to talk about using task load tracking to improve load balancing in the kernel scheduler. We've already had one excellent presentation this morning about kernel scheduling by Preeti from IBM. And I'm going to dig in a bit deeper and look at what we have been working on. So first of all, what is this task load tracking and why is it necessary? Well, I've chosen to call it task load tracking because what we've been looking at is mainly focused on tasks, but in reality it's actually called load tracking per shed entity basis. If you read Paul Turner's original cover letter for his patch set. It means that his patches introduces a way of tracking load for each entity. As we know, entities in the kernel scheduler, that means task groups and tasks. But for today, I'm just going to use task load tracking because it is a task that I will be talking about. It's not currently used for load balancing. It was introduced by Paul Turner to improve group scheduling, but I will talk about today how it can be used to improve scheduling for better power. It's now included in 3.8, so it's no longer a separate patch that you can actually find all the details about the load tracking stuff in the mainline kernel now. If we want to look at what sort of power awareness we have in the scheduler right now, there isn't not much really. We used to have something called SCHED-MC, which used to be able to pack tasks in certain scenarios. That was dropped, I think, about a year ago. So right now we don't have any real power awareness in the scheduler. The load balancer basically balances tasks based on the number of tasks you have on each run queue. It doesn't consider what type of task you have. There's no distinction between task behavior. A task is a task no matter if it's running on the CPU all the time or if it's something that just shows up every 100 milliseconds and just run for a short moment and then goes back to sleep. And the current scheduling policy is just to spread tasks across all CPUs to get the best possible performance. That works well on big servers, but where I'm coming from, we're focusing quite a lot on power consumption. So that's why we have looked at the scheduler and see what can we do to improve this. Well, here's an overview of my talk. I'll talk a bit more about the load tracking stuff that was introduced by Paul Turner, so we can understand better what it can be used for. So I'll go through some of the most basic math in there. I'll try to make it easy to understand, and please ask questions if you have any as we go along. I would much rather have an interactive presentation than just having me talking here for 45 minutes and you checking emails or sleeping or whatever you want to do. So after I've gone through the load tracking stuff, I'm going to talk about two proposed patch sets that I've been involved in developing. One of them is the patch set which packs small tasks. Preeti already described it shortly this morning. Both of the patch sets, both the packing small tasks and the other one which tries to do better on heterogeneous systems. They're both been posted on LKML. I would consider, especially the last one, work in progress. There's still a lot of issues to be sorted out, but that's why I want to talk about it today, so we can get some feedback from the community and we can work together towards a workable solution. And in the last part of the presentation, I'll talk about some of the observations that we have done and what sort of open issues that we're seeing at the moment. So if we look at what task load tracking is, as it is introduced by Paul Turner, it is a way of representing the the execution history of a task in your Linux system. I have tried to illustrate it on this slide. If we take the top graph here, what we have on the x-axis is time. Now is to the furthest to the right, and for each sample is 1 millisecond of time. And the height of the bar is how much of that millisecond that task was actually runnable. And by runnable, I mean either actually executing on a CPU or at least being on the run queue and being ready to execute on the CPU. So for this particular example, we had a task which became runnable about 10 milliseconds ago, and it was runnable for 4.5 milliseconds and went to sleep or got blocked, or for some reason was removed from the run queue about 6.5 milliseconds ago. So we had 4 milliseconds where it was fully runnable for the entire millisecond, and the last one it was only runnable for half of that sort of time slot. And the way we use that in the calculation of the track load is that for each of these time slots, we apply a weight. And that's the weight I've represented in the second graph. So what happened just 1 millisecond ago has a weight of 1. What happened 2 milliseconds ago has a slightly lower weight, and so on. The further back in time our record is, the lower the weight. So you can see, well, what we do to get the track load is that we basically multiply the weight to each of these samples. So we get the result here at the bottom. So you can see that they slightly decrease in value, each of the samples, because we have multiplied by the weight. And the track load is using the sum of all these weighted samples. So in this case, we get something called the runnable average sum. I use the terms here that are used in the actual kernel code. It might not be obvious why they're called this, and if you read the code, it might still not be obvious why the variables have the names they have, but this is the name of the variable in the code. So in this example, the sum of all these samples after we have applied the weights is 3,856. So what will happen is, over time, as this task, well, if it's not executing anymore and time progresses, the track load will be smaller, and that I'll try to show on the next slide. So this is 30 milliseconds later. So we see we have added 30 milliseconds where we're doing nothing. It means that the applied weight for each sample will be smaller. So the weighted history will look like this, and the sum will now only be 2010. So this is sort of the fundamental thing in the track load. You apply a higher weight to what just happened, and over time your history will sort of decay and eventually diminish. Yeah, but this is not the whole truth. But this is sort of the way that we try to remember how a task behaved in the past, and the assumption is that we can use the past to at least come up with a reasonable prediction of the future. Of course, we can't predict what's going to happen, but this is a nice way to capture how the task behaved in just a single variable. All of this can be optimized quite a lot, so it's just a bit of addition. And I don't think we even do multiplication to get this. So it's actually fairly cheap to maintain this load history for each task.
So the time scale needs to be like, when you say 0 is...
Yeah, I should probably have inverted this because now right now is to the right, and 1 millisecond ago is to the right minus 1 time slot. So this is actually 64 milliseconds ago that you have here. Yeah, okay, thanks for asking. Yes, this is not the entire truth. The actual load contribution, as it's called in the kernel code, consists of this weighted load history. It actually also it's actually also based on the age of a task. There is a similar history maintained for the age of the task. It's not really that important, but it has an effect in the beginning when a task is new, when it was forked just a few milliseconds ago, because then we don't have as much history, and this extra age will take care of that. Another important thing is that the load average contribution is actually scaled by something called the load weight. And the load weight is actually already used, or it's been used in the scheduler for years. The default load weight of a task is 1024, as shown in the table here. That's the weight a task gets if it's got a priority of nice 0. If it's got a higher priority, it will have a higher load weight. If it's got a lower priority, it will have a lower load weight. And the load tracking is scaled by this load weight. So where a task in the past just had a static weight when you do the load balancing, which was what you could look up in this table based on this priority, the load contribution is now a value between 0 and the load weight, because the time series is scaled. The load history I showed in the previous slide is scaled such that it will give a factor of between 0 and 1. Yeah, enough about the math. If we look at two examples of different tasks and how the load average contribution looked like, here we have a long-running task to the left. The upper graph shows, again, the execution history. The task is woke up quite a while ago, and it's just sitting on the run queue, or it's executing all the time, basically. And what will happen is that its track load will start from 0, and because it sits on the run queue all the time, it will slowly build up. Because if we imagine this, where the blue one would just continue all the way to the right, the sum will just grow bigger and bigger as time goes on, and the task just keeps executing. So this is the track load you will see on a intensive CPU-intensive task. On the right, we have a short periodic task. This one only wakes up every 10 milliseconds and executes for 1 millisecond. And that means that we'll only add something to the track load every 10 milliseconds, and then for 9 milliseconds, the track load will slowly decay again. So we have this sort of very faint ripple on the load contribution. So what's really important to observe here is that we can actually, based on the load contribution, we can say quite a lot about the task. If a task has a low load contribution, we know that it's not consuming a lot of CPU cycles. Whereas if it has a high track load, it uses a lot of CPU cycles. So based on this single value, we can say quite a lot about each task. And that is what we're trying to use to improve power consumption by making more clever decisions in the scheduler. So let me first talk about the first patch set, where we are using the track load to identify tasks which we believe can be packed. We're considering what we call small tasks here. A small task is a task that wakes up periodically. It doesn't execute for very long. It doesn't have to be strictly periodic, but something that just shows up once in a while, executes for a fairly short amount of time, and goes away again. This sort of task will have a track load which is very low. It will never get very high, and it is a type of task that will disturb our sleep quite a lot if we have an idling system, because if we don't take care of it, it might wake up on any CPU, and at least on ARM systems we have sleep states where we need multiple cores to be sleeping to enter an even deeper sleep state. So if we have tasks waking up at random CPUs, you can actually keep other CPUs in a higher, more shallow sleep state, and therefore waste power instead of trying to coalesce all these noisy tasks on a single CPU, so the rest of them can be in deep sleep for a long period of time. So the proposed solution in this patch set is to try to pack all these small noisy tasks onto as few CPUs as possible, and thereby enable the rest of them to the rest of the CPUs to enter deeper sleep states and thereby save power. Another thing about the small tasks is that because they're executing for such a small amount of time, we believe that the performance impact of packing them is next to nothing. If it's a task that only executes 5% of the time, if you pack 10 of them on one CPU, you should, in theory, use 50% of that CPU time, but it wouldn't impact the performance of that particular task a lot. So, yeah, that's the idea. There is a patch set that's been produced by my colleague Vincent from Linaro. It's been posted on LKML. I think he posted version 3 recently, 22nd of March. It's been discussed quite a lot. I think it works quite well. I'll show you some numbers in a minute. An essential part of this patch is to figure out where to actually put all these small tasks. He's introduced an extra sketch domain flag that will indicate which CPUs that belong to the same power domain, because that's essential for packing the small task. We really want to make sure that we only have one power domain alive if we can get away with that, and making sure that the other ones can be powered off. So what he's done to try to make it as cheap as possible to figure out where to put all these small tasks is that he's introduced what he's calling a packing body. For each CPU, he's got a packing body, which is another CPU where we'll try to put all these small tasks as we see them. If we see a small task which is about to wake up on this CPU and we know that our pack body is not busy, we'll just put it there. And the idea is that you can have a setup like the one I have illustrated here at the bottom. This is a 4-core system where you have two power domains. CPU 0 and CPU 1 is in one power domain. 2 and 3 is in a different power domain. The idea is that, for example, if CPU 3 sees a small task which it thinks should be packed, it can put it on CPU 2, which in turn, if it sees a small task and sees that CPU 1 is not overloaded, it can put it there. So all the small tasks will sort of be packed towards the left until CPU 0 is too busy to accept more small tasks. So in that way, we try to sort of pack them together, and if we manage to get rid of all the small tasks from both CPU 3 and CPU 2, then that power domain can be completely powered off. There's been some discussion about how's the best way to select the body, because if you have CPU 0 being very busy, then you may end up having power domain 1 being active, where it might be possible to actually run the small tasks from power domain 1 on CPU 1, but because we don't check CPU 1 from power domain 1, we'll keep them on CPU 2 and 3. So you could probably improve the packing by letting CPU 2 pack on CPU 1 instead. But the disadvantage there is you can get longer and longer chains of sort of bodies, such that if you start on CPU 3, then you pack your task on CPU 2, which will then pack it on CPU 1, which will then pack it on CPU 0. So you end up migrating the same task 3 times, which is not optimal. So for now, this is the selection scheme that's been proposed, but I believe for some platforms you might want to tweak this slightly depending on the specific circumstances that you have on your system. Yeah.
Could you talk a little bit about how the sched domain flag works? How does that map CPUs to power domain?
The idea is that, well, in the scheduler, you represent your topology using scheduling domains. I can give you an example for ARM. We have a test chip right now where we have 2 clusters. So you have a cluster of 2 CPUs and a cluster of 3 CPUs of a different type. If you, for each cluster, can power gate the whole cluster, then for that domain, you would set this flag and say that these share a power domain. And that way the scheduler would know about if it makes sense to pack inside that domain or if it's useless to pack inside that domain. If you have 2 CPUs belonging to the same domain and you can't power gate them individually, then it doesn't make so much sense to actually pack them. But whether it makes sense to pack inside your domain or when to set the flag, well, that might be platform specific because some platforms might have more efficient power gating per core than others. So it's a bit of a trade-off. But yeah, that flag has just been introduced as a way for the scheduler to know about the power gating capabilities of the platform.
Can you just repeat the part about why you want to just give CP1? Is it, because of the time frame that you're looking at, how long you would end up taking to migrate small tasks, or is it for other?
There's both time, but yeah, it can also, it can take a bit of time to do it, but also you keep disturbing a CPU every time you sort of move it. But again, if it's a small task, the cache footprint and things like that shouldn't be a big issue. So maybe it is okay to have long chains of bodies. But I'm not, it can take a while for a task to actually migrate to sort of final destination if you have very long chains.
We're in the end talking about tasks where you really save this one of these small tasks that's long living. So you would think that eventually ends up where it would end up anyway.
So if it is small tasks that we're talking about, and it is, then I think it's okay to actually have longer chains. But if you try to pack bigger tasks, I think Vincent in his patch had defined a small task as a task which runs less than 20% of the time. Then a 20% task might be, I don't know, more expensive to migrate too many times, depending on the memory and cache footprint. It's a trade-off, what you want to do. So, yeah. I have some numbers here. We've evaluated the patches on an ARM test chip. It's a big little test chip. It has got 2 Cortex-A15s, 3 Cortex-A7s. The fact that it's a big little is not really important for this particular patch set because it will give you power savings on normal SMP systems as well. If you have an SMP system where you can power gate some of the cores and leave others running, you'll get similar power savings. So what we have done here is that we have been running MP3 playback on Ubuntu. That should be a fairly small task to run an MP3 decoder. And what we saw was that this task, and along with all the other tasks running on Ubuntu, because they could be packed to a single CPU, actually saw 36% less energy when using these patches. You can see to the right there is a breakdown of the energy for this MP3 playback. So you see, for this particular platform, we selected the bodies such that the Cortex-A7s, which are power efficient cores, they they were the targets for the small tasks. Of course, we don't want to pack small, noisy tasks on big, less power efficient CPUs. We want to run them as cheaply as possible. So on this setup, the small tasks were packed on Cortex-A7s. And we can see here that the energy coming from the Cortex-A15 is reduced from about 80 down to, I think it's around 15 when you look at the bar to the right. So clearly the patches have correctly identified small tasks and put them on Cortex-A7s, which should be powerful enough to handle small tasks. We also verified that we didn't have any performance regressions by running Hackbench. And we didn't see any difference in performance or variations in the numbers. Yeah, let me continue to the next patch set where we are targeting heterogeneous MPs. And by heterogeneous MPs, I mean multiprocessor systems where you have cores of different types. That is, for example, ARM Big Little. The work here is not specific to ARM Big Little in any way, but I don't know any other system that has mixed types of cores yet, but who knows, it might come one day. What's really important for this type of system is that we can make informed decisions about where to put tasks. Suddenly, it makes a huge difference where you actually place a task, because if you place it on a big core, it will run really fast, but you will pay more energy per instruction than if you were executing the same task on a little CPU. So suddenly you need to consider what type of task do I have, and is it really worth running it faster but paying more in terms of energy? Or is it okay if I just put it on the little CPU? It will take a bit longer to complete, but our battery will last a lot longer. So the strategy we're trying to apply here is to don't use the high performance cores unless it's absolutely necessary, because they will drain your battery faster. And at the same time, we should also make sure that CPU-intensive tasks that really requires high performance, they should also get to the faster CPUs. It doesn't work very well if you don't get a high-performance CPU every time you need it, because then you'll get random performance. As it is, if you just run the mainline scheduler on a big little system, you'll get performance that is somewhere between little and big performance. You can't really be sure, because your task may end up on any of the CPUs. You're not guaranteed to run on a big CPU or on a little CPU. So if you do 10 or 100 runs, you'll get numbers which are varying quite a lot. So that's something we need to address for Big Little. Yeah?
I'm wondering, do you have any metrics or heuristics around the decision, big versus little? You said always try. There's some trade-off there. I'm wondering, do you actually have any encoded metrics to say, if it's such and such kind of thing, then it might be worth running it on a big anyway?
Yeah, the way we do it right now is that we actually use, or the way we have experimented with it, is to use the track load, and basically say if a task got a high track load, which means that in the past it's used the CPU a lot, then we think it's a good idea to put it on an A15, because it will have a big advantage of running on a big CPU.
So you'd say more prefer the kind of processor that the task matches?
Yes.
Okay.
Yes.
And then the other side of that is, I don't know whether your configuration can change big to little. I saw one of the variances where it's pairing a big and a little together, and then only uses one of them at a time. Do you consider the amount of time it takes to switch a processor from big to little, a combination, I mean, in deciding this is basically choosing two problems to solve or one problem to solve? If you look at the static architecture of the system currently and say, how would I schedule for that configuration versus how long would it take me to switch the configuration of the system and then schedule for that one instead? Do you see what I'm talking about there?
Let me think. there are two big little solutions sort of proposed right now. The one I'm talking about here is the full MP solution, as we call it, where we let the scheduler know about all CPUs we have in the system.
Right.
So we actually treat big little as just an SMP system where some of the cores just happens to be faster than the others. We don't do the pairing in this solution.
I'm trying to stretch towards one where you could actually change, for example, a clock rate on one of the cores.
Yeah.
Or, for example, it's off and the amount of time it takes to warm up its L2. Those kinds of questions affect the decision. Should you schedule for a current configuration, or should you aim, and maybe it's a longer tracking thing? After you see the task load evolving this way, you say, maybe I could use another core.
Yeah.
And can I use some help? Right? Kind of like a hiring process outside the system that brings on more, or says, hey, we can put somebody in warm down mode.
Yeah, it does actually make sense. I think if you have, for example, all your big cores powered down, it will take a while to power them up.
Right.
At the moment, we don't consider that overhead, but it could be something we should consider, because if we detect a task on a little CPU and say, okay, this one should really be running on a big CPU, if we just tell the scheduler to move it now, and we don't take into account that the whole big CPU cluster is actually down, it might have to wait a while until it can actually run on that CPU.
Yeah, I think general feedback I would have is that I see the trend, and I like the trend of using more information to give the scheduler to make better informed decisions.
Yeah.
But I still wonder how many different problems there are to solve in parallel and let the systems inform each other. Right, so
Yeah.
we look at the ACPU clock, and we look at power management, if we look at scheduling as independent problems, and figure out how to inform those different subsystems to each other to make sure that they line up in the long run.
Yeah, I agree that there is a lot of coordination to be done between all the power management frameworks. CPU idle, there was a guy proposed.
CPU one of them. Yep.
CPU idle is one of them. CPU freight is another one, and I'll actually get back to that, because that gives us some problems with the track load, because when you vary the compute capacity of a CPU, you actually mess with the track load. If you have a task which is running on CPU at a low frequency, it might have a high track load because it uses the CPU quite a lot. Whereas if you scale up the frequency and you don't take that into account, the load will actually appear smaller because you have more cycles per second on that CPU.
Comment made earlier in the morning session about using a feedback loop. And I guess it's perhaps a value-add comment here. Are you using any hardware feedback mechanisms here, performance monitorings or so forth?
Not in the current patches, but we are internally exploring using the performance counters we have various performance counters on ARM that are quite cheap to sample. So we have experimented with actually tracking as part of the task struct. We add a lot of metrics about how has the task behaved in the past. The difficulty there is to find good counters that we can use to actually make good decisions, because in complex microarchitectures, some of the counters, the events that you're getting might not tell a full story, so it's quite hard to interpret them. But it is something that we're looking at. One thing that could be really, really useful is that if we could see the cache footprint of a task, but that's extremely hard to derive from the performance counters. Because, yeah, you can see the cache miss rate, but it doesn't tell you anything about how many cache lines you actually use in the cache.
I was frustrated by that this morning. I think someone used the term CPU affinity as an attribute you assign. I'm more interested in knowing how attached to the CPU the task has become. In other words, a discovered affinity.
Yeah. That is something that one of my colleagues have tried to derive, but it's quite difficult. There are some research papers actually on estimating cache footprint based on cache miss rates. The problem is that when you increase the associativity of the cache, it's almost impossible to derive anything because you don't know how many cache lines you have belonging to your task. Yes?
I think it brings up an interesting question now, like your track load, does it take into effect, or does it take into the consideration of your heterogeneousness of your code, right? So the track load on small CPU.
That is another thing. As I said, there is a problem already with frequency scaling because your track load will look different if you scale down your frequency.
It's not the same load, same weight.
Exactly. So, what we're proposing to do to fix the frequency problem is to basically scale the track load by the ratio of the max frequency you're running at. So you sort of make your track load frequency invariant. And you can extend that even further by scaling by the microarchitecture difference between the big core and the little core. But it's a bit more difficult because you sorry?
Is it a BOGO free?
Yeah, but it will be way off in many situations because it's not a fixed ratio. If you benchmark the A7 versus the A15, you can get more or less any number you want.
So frequency is not the only difference between big and little, right? So
No.
it becomes more complicated.
But we might get some of the way by just picking a reasonable number and then just treat the track load as being something which is inaccurate. It's better than nothing, I would say. Yeah, well, lots of things. The track load isn't accurate in itself either. So it's all heuristics, yes. It will never be perfect. Does that answer your question? Okay. Yes?
So it was building off the same thoughts and same discussion, but I'm just curious, and I think you alluded to the heterogeneity could extend to execution units and how many instructions you can use and whatnot. But I mean, I find myself thinking based on this morning's discussion, is some of the power efficiency due to less cache transistors as well? I mean, are you going to not only run into a problem where you're packing potentially higher cache footprints, but the lesser CPU, or the lower performance CPU has less cache to begin with, which you normally can query at least, so you could take that into account in your scheduling weight.
Yes. For the big little test chip that we have used to evaluate these patches, there is actually different level 2 cache size. You have a separate level 2 cache for each of the two clusters. So the big CPUs have a level 2 cache, and the little CPUs have a level 2 cache.
L3 shared or no L3 at all?
There's no L3. And they're actually different sizes. So yeah, there is a problem there as well.
Have you run with workloads such that when you pack, you'll overflow the lower to see the perturbation?
We haven't done much research in the cache footprint yet. We have mainly been focusing on just saving power and getting performance fairly consistent because, yeah, the first thing we saw when we started running Linux on Big Little in sort of SMP mode was that if you run the same workload 100 times, you get any performance number between just running it's purely on a little CPU or exclusively on a big CPU. You can get any number in between. So that was the first thing that we wanted to solve. So, yes? Mm-hmm. Sorry, I didn't get that.
So the pattern small tasks packed by reason.
Yes?
Does it, when it chooses the CPU hardware body,
Yes.
does it choose it based on if it's a big CPU, a little CPU?
Yes.
Or is it completely independent?
At the moment, as far as I remember, the body selection algorithm that is implemented actually checks the CPU power of the CPUs. And it looks inside other scheduling domains, and if it sees a CPU with a lower CPU power, CPU power is used in the scheduler to represent the compute capacity of a CPU. And if it sees another CPU with a lower CPU power than itself, then it assumes that that CPU is more power efficient, and it will use that as the packing body. So the body selection algorithm that I showed you before will actually pick a little CPU as its packing body by default.
Another question I had was with regard to what you said. Why does the task entity load tracking need to take care of CPU frequency adjustment?
Because if we go back here and say we have a task which runs, well, this is probably not a good example. If we have this shown periodic task here, for example, which runs 1 millisecond every 10 milliseconds. If we reduce the CPU frequency to 50%, say we were running 1 gigahertz for that, if we reduce the frequency to 500 megahertz, what will happen is that the task still needs to do the same amount of work every time it wakes up. So now we'll be running for 2 milliseconds every 10 milliseconds. And that means that the track load will actually be twice as high because it's runnable for twice as long per 10 milliseconds. It depends on what sort of task you have. If you have a task which is set off every 10 milliseconds, if you're doing video decoding or something, which is periodic, you need to render a frame every 16 milliseconds or what you're doing, then the amount of work you need to do every 16 milliseconds is the same, no matter how fast or how slow you run your CPU. The difference is just that it may take you 2 milliseconds to render your frame if you're running at a very high frequency, but if you run at a low frequency, it might take you 5 or 10 milliseconds to do the same job. And if you don't take that into account in the load tracking, then your track load can be anywhere from 15% up to 50%, depending on which frequency you are running.
It has a trickle-over effect as well. If you have a task which is currently using the only CPU and it's running at half rate,
Yeah.
all of the other tasks which are runnable will be runnable for twice as long.
Yes.
Right?
Yeah.
You have to have semantic separation between best effort and real time. Because when you start mixing those two, then it's just a little weird. It's the concepts start failing. Because you start proposing deadlines on the best effort system. And all of a sudden, look, the logic is not set up for that. Certain CLS is not set up to make this calculation.
No.
Because all the interactivity boosters and all those things are not appropriate for this situation. They don't know about each other's rebalancing. So the rebalancing mechanism in CFS is a variant of super great wrong top view. It's very closely related to that. And the real-time scheduler has a totally different rebalancing mechanism. They don't know about each other. So all of these things have to be considered in real calculations. It makes it, it argues for a different configuration of scheduling. It argues for a different scheduler other than CFS or the kernel scheduler. And that's all I'm saying. It really does.
Yeah,
Yeah.
I'm not sure which parts of that about CFS I do or don't agree with, but I would like to say that the current sort of simple-minded view of optimizing power is that the sooner you get everything done, you can go back to idle, means that real time is helped by best effort. Right? Because we really are, if you had some cores and you could use them, then you would wake them up and use them. So in that sense, at least, you try and get things done as soon as possible is at least better effort.
Yeah.
Yeah, I'm going to have to say that they have to be separated. They really need to be separated. Because if you deal with an audio chain, you have determination that decreases as the audio chain gets longer. So you have hardware, the hardware will be running at, like, say, 30 milliseconds for a sound card. That's very deterministic, right? You might have a mixer. The mixer might be very deterministic because the fixed data is used to calculate and multiply that, right? And as you go farther out, you start dealing with codecs with one limit algorithms. You start getting a lot more determinism. So you have to mind do thoughtful or things like that. If you don't know the upper bounds of those tasks, you're never going to meet those deadlines. You're never going to meet the requirements of that. It doesn't matter what your best effort system does. Best effort is inappropriate for real-time scheduling. So those balance, those road calculations have to be separated, and it argues for using a global schedule. And that's something that people don't want to talk about, but this is something I've broadly considered for a long, long time. I talked to some people about it. You have to start considering global scheduling, and you have to start thinking about changing fundamental ideas about what people think scheduling is. And the CFS is not like a Bible of schedulers. I mean, there's many people that they have many, every for what's the line about opinions and assholes? Everyone has them, right? So like you have to start considering breaking up things like load balancing and finding out what's appropriate and wondering if link semantics are appropriate for the kinds of decision making people are doing on ARM architecture, things like that. And that's all I have to say. Forceful man.
Well, yeah, actually, that's another interesting part. I would like to give positive feedback to this morning's discussion. The idea of buddy packing tasks which have similar behavior, I think, also addresses this problem, in the sense that periodic tasks are often the ones that may be real-time in nature, right? Things that handle a certain sampling rate, and if they can find each other and essentially have buddy affinity, and all find the right same CPU and work there together, they may be helped by staying on a little CPU away from the big guy, which keeps on coming in and doing weird stuff on the GPU at random frequencies. So I think there are aspects of noticing the behaviors of the system to make the scheduler help that happen, rather than trying to do this kind of hard hammer kind of approach of either setting affinities or saying there's a real-time scheduler versus a non-real-time scheduler. So
you're mixing up two things. You're mixing up best effort and admittance policies. Those things have to be separated. If you read the Carnegie Mellon research papers on resource reservations, they have specific policies that dictate the parameters in which processes execute. If you don't know where the upper bounds of a process executes, you can't apply, best effort algorithms in order to say, a buddy chain or whatever it is of execution. You have to characterize the task you're running first, which is the intrinsic property of the real-time task, which is ignored in this kernel for the most part. Because it's arguable how real-time the real-time schedule is in the actual Linux kernel for many reasons, right? And it has nothing to do with the preemption patch. Those have to be characterized before you can even talk about the other stuff. Those are the known bits. And if you can get those things knowable, then within the domain of real-time scheduling, right, with the kind of upper bounds of execution, you can play with that. Now, a lot of people in research groups are playing with that in Italy, and University of North Carolina, Chapel Hill. People are playing with these things. But the semantics, in my view, right, as a person that's relatively not involved in this paper, has different ideas from a different community, right, is that you have to define those things clearly before you can discuss what the kind of load balancing, kind of load balancing methods can be. So all those categories have to be characterized, the terminology has to be defined, and then you have to characterize all those things and how they interact with each other before you can start discussing the load balancing issues. And that's my opinion.
More these patches, do these primarily do these address all tasks on the system, or do they strictly sched other tasks?
All of this work is focused on the CFS scheduler, so it's not real-time tasks. If you're running audio or video decoding as a CFS task, a sched other task, then you should know that nothing is guaranteed, and that's how we're approaching the problem right now. Solving.
Probably don't want to bounce between cores anyway. The real-time task.
No. Well, right now, I think if you use real-time tasks, you should know what you're doing, because you can really mess up your system if you run something as real-time. There is a weak link between the real-time scheduler and CFS, but they don't really know what each other are doing. Completely agree. Yes.
The concept of load balancing is only in CFS schedule. What I mean is, load balancing happens only for the normal task. It doesn't happen for real-time tasks. Real-time tasks have its own way of distributing data. So whatever happens here, the load tracking or risk patterns have not been applied to real time, so we will not be disturbing it. Even the morning session was on the non-real time tasks. We will let the real tasks handle themselves the way they are doing. And I don't think they even know about the APCPs when they're doing real time task scheduling. They don't even know about the Yeah, it balances by priority, and all of them are the ones, the real time tasks are taken care of first, even before we come to the balancing of the non-real time.
There's a side effect of interaction between the shared resources. And that's why, the splitting of the sketch classes is useful for coding and simplifies things, but there's no unified method of load calculation across both schedules. Technically, you can have another scheduler that is soft real-time operations between those two classes, and they would not know about it. It's a structural problem with the code itself, and the abstraction of the class sketch hierarchy, the sketch class object model that currently whatever the implementation is not incorporating load calculation across all effects.
Why do we want to do this?
You want a global schedule. You want potentially, right? This is theoretical. This is sort of a presumptuous thing. You know precisely what the arrival and departure of the CPU of threads across on a CPU at any given time. So this thread needs this processor at this particular time. We call it processor N, right? I know that processor is idle, and I can pick it off the global run through the line. You can't do that in CFS easily. You have to distribute that across a CPU scan, across the entire CPU. So that's going to create a certain kind of lag balance between the algorithm itself. With the global scheduler, like this theoretical, talking about this in theoretical math, right? And I know people have experimented with this stuff, right? And they have various things we can talk about if they're not used, right? Is that if you know what the precise load calculation is, right? You can have the load calculation. You know exactly what's going on with the CPU. You can do precisely what's appropriate for the CPU at a given time. So you might have something at a different clock rate, right? Well, if that CPU is at a different clock rate, then maybe I can grab this global lock and I can check the CPU governor and decide which CPUs are idle that I want to schedule this thing to, right? Schedule this process to. And it's useful to have that in a single sort of like incoherent. It's useful to see a snapshot as to lock in time, so you can know what to do with that at a particular time. And that's what I'm trying to say. It's something to consider. It's not a religion. It's not like anything is right or wrong. It's like these are things to consider if you want to do power management. And ARM is particularly weird about it. It's not like Intel or anything else. So these are ideas that I play with. Other people play with. You might want to talk to some.
Okay. Well, thanks for your input. I don't have much time left, so actually, I just want to show you that that the patches where we're trying to do something clever when we have big and little tasks on a big little system, they basically just look at the track load and see, okay, this task has been using a lot of CPU time in the past. Let's put it on a big core. If it didn't, then put it on a little core. Then we can actually get, I'll just show you the numbers. We can actually get quite good power consumption, or when we use this patch set, and also get quite nice and consistent performance. One thing I would highlight here is that we've run a number of benchmarks. One of them is sysbench. We just run one thread of sysbench on our big little test chip, which has 2 big CPUs and 3 littles. And if you don't do anything, that is the dark blue one, you get, lower is better. This is performance, all of this. Then you can actually get a saving of about 34% if you make sure that your task is always placed on a big CPU versus being placed on a random CPU. So really, we need to make sure that we put the tasks in the right places. Because, well, what you can't really show on a single graph is that if you do 10 runs, then you get good scores sometimes, worse scores other times. We need to get it consistent, because otherwise you won't get consistent performance on your smartphone, for example. The patches on LKML, there is a link in the slide somewhere. Here. I think the slides are online, so you can find it and have a look if you want. I'll skip to the things that we think are important to address in the future. That is the frequency scaling. We already discussed that quite a lot. Another thing that we haven't discussed is, well, it's fine if you look at a task and see it uses a lot of CPU time, and we can put it on a big CPU, but what if that task didn't really matter to us? What if it's fine, it takes 4 seconds to complete instead of 2? We don't really care if you're indexing your email in the background or something. We don't want to waste energy doing that. There's no way we can see that from inside the kernel, that this task doesn't really matter. We toyed with the idea in the beginning that you could use priority to indicate whether a task was important or not, but that was not very well received in the scheduler community to use it for that. So right now, I think the only way you can really control that is if you set the affinity explicitly for a task. You can use C groups or something like that to pin your task. If you have a task that you know it doesn't matter when it will finish, then just pin it to run on a little CPU, because we don't know from inside the scheduler whether the task is important or not. We need to rely on the middleware to do that.
So that only matters if the performance versus power is not linear, right? If something is going to take a certain amount of time to complete no matter what, let's say I start some background task, again going back to the point I made earlier about the sooner you finish it, the better, right? Because most of the low power states require turning everything off, right? You got to turn off all the CPUs and the L2s, right? So in that sense, kind of as long as it's not doing anything else, you may as well hurry. You may as well just go ahead and index your email in the background as fast as possible. Agreed, interactions between, handling touchscreen events is not the same thing. But still, you may as well just keep on running it.
But your energy per instruction is much lower on an A7 than it is on an A15.
Yeah, again, so that's why I'm saying A7 versus A15, I'm not sure what the performance versus power trade-off is there. But the long-term payoff of getting it done on either one, so that you could shut down both of them, probably still wins, doesn't it?
I'm not so sure. It also depends on how much I/O you're doing, for example. If you can't fully utilize the A15 anyway, because it's waiting for memory or disk or whatever you're waiting for.
Yeah, it's a good point. Like Unreal time is maybe a good kind of third task to consider. Right? I don't really care how long it takes. Just finish it eventually.
Yeah, true. So, yeah, that's one thing. The other thing is that if you have a multi-threaded workload where you have sort of a whole chain of depending tasks where each of them is quite small, then you might actually sort of bypass this whole thing and if they all add up to being something that would be considered a big task if they were one task, but now we have 5 tasks doing the same work, then as it is right now, they wouldn't be considered as something that should be running on a big CPU. So in the future, we might want to look into how we can maybe group tasks in a way that we make sure that you get good performance if you have something where you have long chains of depending tasks. It's quite hard to see from inside the kernel, so it might need some input from middleware to do that.
I had a question. You mentioned IO. So have you guys done anything on your talk that talks about how you take a task and change its CPU affinity? But for IO you have cards. They also have a CPU affinity in terms of where they send the interrupts. So as you try to take tasks off of certain CPUs, do you do something similar on the IO side to get the cards to also start sending their IOs and their interrupts to different CPUs?
We don't move the interrupts as it is right now. So you may have your interrupts happening on one CPU and the actual data processing happening on another. One thing that we actually found out with the big little test chip is that it's really important that you make sure that your interrupts go to a little CPU by default, because otherwise you keep waking up your big CPUs, and that's really, really expensive. So to get good power consumption, then you actually need to make sure that your interrupts are handled by default, at least on your little CPUs. But it might have a performance implication, yes.
Right, and for example, IO, your cache is sitting or is moving around.
Yeah.
Whereas your interrupt is going to, like you said, little CPU and then
Yes.
handle how the process. Yeah.
So, but it's something we need to look more into. We have mostly studied Android workloads because that's the obvious target for Big Little in the first round. And there we haven't seen any major performance impact of doing it that way. But of course, if you have different workloads, then it might not be a good idea.
Would you say these are high IO workloads? Or?
Yeah, clearly, if you have your interrupts happening on one cluster on a little CPU and you're doing your processing on a big CPU, that would not be good for performance. Yeah, I think that's it really. An obvious next step would be to start considering slightly bigger tasks, not just the small ones and the really big ones, but the ones in between, and see if we can do some packing with those. I know that Alex Shee's patches are trying to address these tasks as well. I find that it's more difficult to pack sort of medium-sized tasks, because if you have a medium-sized task where the track load is somewhere in the middle, is it because it's a medium-sized task, or is it because it's a little task that is about to change to become a big task, or the other way around? So we might not have all the information in the track load that we need to make a good decision there. And when we're looking at Android systems and the track loads that we're seeing there, it's not so clear. It's easier to just put very small tasks in one bucket and then the very big tasks in another one. What happens in between is more difficult to say anything about, but it's something we need to look into. I think time is up, so thanks for listening, and if you have any more questions, just please ask and find me. I'll be here tomorrow as well, so I'll be happy to hear your opinions.